Right, so this video is going to cover bonding from the Unit 1 part of the AS course. It's not going to cover intermolecular forces, hard word. It's not going to cover that. There's already a video for that. It's also not going to cover shapes, molecules. Again, there's already a separate video for that. It's going to really look at sort of the classic examples of bonding, which are really ionic, covalent, and metallic. So which is very much a repeat of everything that you would have done. I'm assuming if you have obviously done GCSEs, but it's very much a repeat of what you would have done at GCSE. And there's sort of a few tweaks here and there, but mostly it's very, very similar. To crack off before I actually get on to how I'm going to do this in the majority, to start with, I'm going to leave metallic. I'm just going to touch on ionic and covalent, because it's a key point to sort of raise here is that the reason they occur is due to differences in electronegativity is sort of the reality of it. So if we think about ionic here, large differences in, which I'll abbreviate to electronegativity, and here we say small differences in electro. There is a way of working out at which point it becomes ionic and covalent, but I can't for the life of me now remember what it is. It might be it's sort of like a difference between the two. I can't remember. I'm not going to pretend I remember. I can't remember at all. You don't need to worry though about that, because the sort of the main thing really, as a rule of thumb, metals and non-metals are going to be ionic, non-metals are going to be covalent. But when we actually think about that, metals and non-metals, metals tend to have quite a low electronegativity, non-metals tend to have quite high, so therefore we have large differences when we bond together a metal and a non-metal, leading us to our ionic bonding, which is quite useful. So, and the other thing to mention at this point really is that as a starting point, I guess, AQA and I guess sort of the big wide world like to refer to these guys as sort of as crystal structures. So if you see the term crystal, don't suddenly panic and die. It's just a way of sort of describing, we have ionic crystals, covalent crystals, metallic crystals. That's the only thing sort of to make of that. I've made this table, the aim of this being that kind of it will contain all the information that you need in relation to ionic, covalent, falling into macromolecular, ignore the little hyphen, molecular and metallic. So without further ado, I'm going to crack through this. I'm going to go quite quickly on this, because I don't want to spend sort of weeks sort of just labouring points that don't need it. Ionic, so what is the bond? The bond, well, actually no, I'll come on to that in a second. The bond is between, as I just raised there, metals and non-metals. Obviously, large differences in electronegativity there, causing us to have this this ionic bond. Here, we just have non-metals. Okay, they could be different non-metals, they could be the same. Carbon forms a few allotropes, which are substances made of only, in that case, the allotropes are just substances made of carbons, graphite and diamond, for example, or graphene, all those things. It could be something like carbon dioxide is also covalent, but obviously different elements in that case. Metallic, we're dealing with just metals there, so whatever it be. And I'll look at some examples in a second. The bond is what? Well, here, ionic. The bond is the electrostatic, I'm just going to, I will write it, the electrostatic attraction between positive, actually no, hold on, a bit better, oppositely charged ions. So it's between oppositely charged ions. Here the covalent bond is a shared pair of electrons. That's very specifically a single covalent bond, not a double. Double would be two shared pair, amazingly. Metallic bonds here, quite similar to the ionic. We have attraction again between, it's my new shorthand if that exists, and I've just made that up, I don't know, between positive ions, which are these metal ions, and negative delocalized electrons, which come from the outer shell of the metals, okay, which I'll touch on again later on in a slightly bit more detail. Examples of each: sodium chloride being our classic ionic substance, sodium chloride. Macromolecular, there's a few that you need to know here too. Diamond, or silicon, also falls under the macroelectric thing, or silica, which is not exactly like silicon dioxide, and graphite. So again, very GCSE, same things there. Molecular, the one they want you to know is iodine, I2. Okay, so that's iodine. And in terms of metallic, it's specified that you know about magnesium, which is fairly sort of straightforward. So that's what we've got so far. Bonds, sorry, what the bond is, what the bonds are between, and examples of each. I've, again, so prepared. Look at this. That is an absolute dream. Sodium chloride, what does it look like? Well, it looks like this. We have alternating, and I've drawn it out in a couple of ways, alternating positive, that's supposed to point to the purple, and negative charges, I'm not going to label every one, forming this big, huge, giant Ionic Lattice. Nice. This is what it would look like on a 2D structure. If you were ever asked to draw it, we've got negative, positive, positive, negative, negative, positive. So we've got opposite charges on every direction. Obviously, you could expand it further and further and further and further. Be pointless to. Don't need to do that. Looking at covalent, then we have diamond. This particular structure here, where we've got each carbon bonded to 4 others. So carbon, 1, 2, 3, 4 other carbons bonded. So carbon bonded to 4 others. Here, graphite, slightly different. Carbon bonded to 3 others. And that is within the layer. Okay, this is the layer. In between this, we have weak intermolecular forces between the layers. Going back to diamond here, we have no intermolecular forces. We only have these properly super strong covalent bonds, all covalent bonds all over the place. Here, loads of covalent bonds within the layer, not between the layers though. They are only weak intermolecular van der Waals forces between the layers there. Obviously no hydrogen, no permanent dipoles. We've got weak van der Waals between the layers, but we have very strong covalent bonds in the layers, and these properties all lead us into, these structures all lead us into what the properties actually are. Iodine here, again, strong covalent bonds in the molecule between the I2, okay, between that, okay, strong covalent bond, but between we have these weak van der Waals. So at GCSE you called them just weak intermolecular forces, which they are, but they are specifically, we are talking about van der Waals forces there forming between our iodine molecules. Okay, very easily broken. Over on this side, magnesium, we have ions, metal ions, and I've arranged it as it would be. Nice regular lattice here. We've got layers of these ions. We have, in this case, we've got the 2 plus ions, boom, 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 and we have delocalized electrons all over, a sea of delocalized electrons. The thing worth pointing, as I said I would do a second ago, is that these delocalized electrons come from the ions. So what were magnesium atoms, each one has lost 2 electrons, or its 2 outer shell electrons have become delocalized within the whole structure. So we have these electrons floating all around, flying through, which leads into its properties again. And on that note, what properties do we have? Well, ionic substances, and I'm talking general ionic rather than just specific to sodium chloride here. We have high melting point, classic one, again GCSE style there. We have electrical conductance when molten or in solution. Reasons for this high melting point. Why do we have a high melting point? Well, actually, tell you what, I'll go through all these and get the properties, and then I'll come back and we'll look at the sort of what's going on. Or will I? No, I'll do it one by one. So, high melting point here. Why? Well, as we've already said, we've got a strong attraction between oppositely charged ions. Lots of energy to break. Could lay this out slightly more clearly, but there we go. Why electrical conductance when molten? Well, or solution. When solid, these ions are all held really rigidly into this giant ionic lattice. They cannot move. As soon as we melt it, or we put it into solution, then we end up with the ions are free to move, and so can carry the charge. Quite useful there. Okay, so ions are free to move, so can carry the charge. Here, graphite. Sorry, not graphite, diamond. So diamond and silica first. Do them here. What properties do we have? We have high melting point. Well, why? Well, we have lots of strong covalent bonds, lots of energy to break, and that's all melting point is. It's the energy required to to separate these bonds, or to sort of partially overcome them. It's requiring a lot of energy because there are so many and they're so strong. Hence the reason that diamond is so strong. This is high melting point actually, and also the fact that it's strong or hard as well. Okay, strong or hard, all the same points there. Diamond, besides that, I'm not going to worry about any sort of other particular properties. Going to go to graphite here. So graphite, what properties does it have? Well, within the layers, okay, and it generally speaking has a high melting point. So I'm going to, same thing applies there, same high melting point, lots of strong covalent bonds and all the rest of it. But the main ones for graphite really that you're more than likely going to come across is the first one, it being slippery, and so it's used as a dry lubricant. It's not an oil. It can be used as a powder, a lubricant powder, within engines and things, particularly where the temperature gets very high, because it has such a high melting point. Whereas an oil might combust or evaporate or whatever, this guy's not going to. It's going to stay as a solid, and it's going to certainly use those lubricating properties. The reason it has those is because our carbons exist as layers, and between the layers we have weak intermolecular forces. So weak van der Waals between layers, and so the layers can slide, which obviously allows us to have this sort of slippery nature. The other thing, and I'm probably going to have to go down here now, yeah, I'll have to, is that they conduct electricity. And the reason for that is that I said here that carbon was bonded to 3 others, whereas we've got 4 here, and carbon normally makes 4 bonds. That means that we have 1 spare electron here that's not being used, and not a non-bonding electron, a single lone one. That electron becomes delocalized, and that can obviously move throughout the structure. So our delocalized electron flies all over the place, boom, straight away we can conduct electricity. This one here, so that was our macromolecular covalent. Our simple molecular, or just molecular covalent, we're talking, main one here is it's got a low boiling point. Reason being weak van der Waals forces between molecules, very important. Little energy to break. Okay, little energy required to break them, which is fair enough. Bit more on the metals here, but there's a lot of overlap with these points. Here, metals, we've got high melting point. Same reasons before. Strong attraction. I'm not going to write it all, but strong attraction. Actually, I will. Between positive ions and negative electrons. Lots of energy to break. Here we then have electrical conductance. Again, same thing as with graphite. Delocalized electrons move throughout structure. Finally, we have malleable or ductile. Very specific this to metals in that these layers, although again similar to graphite, the layers of ions can slide. So these guys can move that way, we can move that way. That means that obviously we can shape it, and you know metals can be shaped into all sorts of different shapes now, sculptures, car body parts and all that stuff. Same applies to ductile. So malleable is the ability to be shaped really, so metals are easily shaped. Ductile means they can be stretched into thin wires. Same principle, the layers can slide over each other. That's why we alloy metals, by adding in different sized atoms of carbon or whatever. We alloy the metals and as such we disrupt those layers. That's very GCSE again. What's good about metals is that once we've reshaped these, actually the reshaping, it still retains all its strength, because we still, the bonding here, the metallic bonding, is the strong attractions between the positive ions and negative electrons. Well, that still exists. We have the same metallic bonding throughout the entire structure, even when it's been shaped, and that's a very, very key thing, which means it's still strong when shaped. On that note, ionic bonding, actually quite brittle, because if you shift these, if you can shift some of these across, you end up with repulsive forces, positive on positive, negative on negative, and actually you can cause it can kind of shear and shatter as a result. So metals very, very malleable, ionic substances quite brittle. That's pretty much the properties and all the general sort of bonding done. So again, just to show you that, so you can pause and copy stuff down if you want. Bonding between metals, non-metals, metals, non-metals, non-metals, metals, etc. What the bond is, examples of each, what it looks like, and then properties. Quite a lot of stuff on properties there, which I apologise, but there we go. The last thing I want to touch on before we do some exam questions is dative covalent bonding. So I'm going to go over here, pick a nice little new colour. Thinking nice pink would be good. So dative covalent, or what can also be called co-ordinate bonding. Love that. It's better to do this with an example. The example that's quite a good one, which you could even get in an exam, is ammonia with a hydrogen ion, and we should note that forms as the ammonium ion. Well, if we drew this out and thought, well, what's going on here? What is happening? Well, here's my hydrogen, okay? It's got no electrons at all. Here's my nitrogen with my 3 bonds, NH3, and I've got a lone pair there. Now, I need to form a bond. It's going to be a covalent bond that's going to form between these two things, but hydrogen's got no electron to share. Luckily, though, nitrogen has 2. So, what nitrogen can do is it can basically, it can donate, if you like, both of its electrons to the bond, the end result being that we form this guy here. So we form a normal covalent bond, but both electrons have come from one atom. So in this case, both electrons comes, well, should be just come, shouldn't it, rather than from nitrogen to form the covalent bond with hydrogen. So both electrons have come from the nitrogen. It's about really in an exam situation, and I've got one question coming up in a second. It's about really sort of realising or noticing what's coming from where are the lone pairs going from and to, and what's accepting, what's really donating, what's got the lone pair, and what can accept that. That's the key thing in an exam. The process is always the same. Say where it's coming from, where it's going to, and use the phrase lone pair in there as well, and you'll be absolutely fine. So, going to look at some exam questions now. I've got 5 separate papers I want to look at. Quite a bit there on the question front, but get through it and you should see how these ideas from this video tie into the actual exam. Okay, so first paper. This is from June 11, I believe. It's question 3D, and it's asking a molecule of NHF2 reacts with a molecule of BF3 as shown in the following equation. Now this is straight away one of these dative covalent questions. Scroll down, so I've got a bit of room to sort of do some bits and pieces. That should be right there. So this NHF2, well, think about ammonia being NH3 and what I drew earlier on. So here's my NH. There's my NHF2. Same idea, lone pair. Here's my BF3. There's my dative covalent bond. So straight away, name this type of bond. Dative covalent. I think my computer's on the verge of dying. How the bond is formed. Lone pair from nitrogen atom. The one right there forms covalent bond with boron atom. And obviously what we'd end up with is a bond between here, which would give us this F2HNBF3 molecule. Two reasonably sort of easy marks there. Switching papers now, Jan 13. Question 3b, state the type of bonding in lithium fluoride. Well, I've got a metal and I've got a non-metal. So boom, straight away I've got ionic bonding, large difference in electronegativity. Electrons have been, transferred and we're forming ions. Why is a lot of energy needed to melt a sample of solid lithium fluoride? We're basically just regurgitating it, we're vomiting on the page what you've already learned. So the explanation, strong, we use good words, strong electrostatic attraction between oppositely charged ions. You can say between positive lithium ions and negative fluoride ions. I prefer oppositely charged. It just cuts that sort of out. Lots. Oh, in fact, actually, it's not. You don't need to put that. It's already saying explain why a lot of energy, so I don't need to say lots of energy. Marks here, you're going to get one for strong, and I guess the other. I haven't got a mark scheme on me. The other one's going to be electrostatic attraction, obviously. One for ionic there, giving us 3 quite tasty little marks there. This is one of those that I spoke about a bit ago. Deduce why the bonding in nitrogen oxide is covalent rather than ionic. So we've got 2 non-metals, but why is it covalent? Well, small difference in electronegativity. I'll write it all out. One more mark. It's about realising that, and some of this you can kind of work that out. I mean, deduce can almost imply work out for yourself what do you think the answer is. But obviously there we go. Small difference in electronegativity. Another one, type of crystal. See, they're loving this word here. What's the crime for crystal shown by OF2? Well, we've got non-metal and non-metal. I'm going to have covalent. Going a little bit more detail there, covalent particularly, we're going to be looking at molecular here. So this small molecule, we can see only 3 atoms. And I should have said that really earlier on, as opposed to my diamond where we've got, these sort of huge number of atoms and all the rest of it. We've got billions of atoms in a chunk of diamond. Here we've got very, very small numbers, so it's covalent. It's going to be molecular, and I'll sack this question off there. June 10, question 7. Later on in the paper, this one worth a few more marks, but same idea. State the type of crystal structure for each of iodine and of graphite. Well, iodine, again, molecular, covalent. Here we've got obviously macro, molecular, 2 marks. I mean, why are they giving you 4 lines? I mean, how big are you writing this? Like, oh. But anyway. 7b, describe the structure of and bonding in graphite and explain why the melting point of graphite is very high. Straight away, what's the structure of in graphite? Well, we've got layers of carbon atoms, each carbon covalently bonded to 3 others. In a question like this, I would just go absolute annihilation. I'd just get everything you know down, obviously within a nice sort of well-written prose, but I'd just absolutely hammer it. Don't try and think, oh, I'm going to write 4 points, because you don't know if you're going to get the right ones. Say what you know. So layers of carbon atoms, each carbon is covalently bonded to 3 others. Between layers are weak van der Waals forces. Why is the melting point of graphite very high? Covalent bonds are very strong and require lots of energy to break. About 6 marks worth of stuff we've written there. You're going to get 4 marks. I think it's 3 for that, and I think it's 1 for that. I haven't seen the mark scheme before. Oh, look at this one. Why does it vaporize when heated gently? Weak forces. Oh, actually, that's rubbish. Weak van der Waals forces between molecules require little energy to overcome. 2 more marks. Delightful. Stable iodine is a very poor conductor of electricity. This one, think about iodine. We think we've got this molecule like this. There's my I and my I. I've got no free electrons. I've got no ions. So no free, or delocalized is a better term. No delocalized electrons and no moving. Well, we'll set that off actually. No need to say about ions obviously because we've got a covalent substance there. So not really any point. So that was June 10, that paper, question 7. Going to go on to June 12. Another similar one here is question 4. Yeah. This time, using this new thing, graphene. Doesn't mention anything. You might think, well, I've not gone through graphene. Well, you look at the substance, having this very distinct substance here, or the structure, sorry. Each carbon, it does say it's made from carbon atoms, bond to 3 others. This is just a layer of graphite. Okay, and this genuinely is a real thing as well. They've not made it up for the exam. Graphene is exactly as it says, excellent conductor of electricity and all the rest. Now I can see, before I look at the rest of the question, they're stating high melting point and it's an excellent conductor. I guess they're probably going to ask us, why does it have a high melting point and why is it an excellent conductor? And there you go. So what's the type of crystal structure? It's macromolecular. You can also say giant covalent. I just prefer macromolecular. I like the word macro. Suggests why graphene is an excellent conductor of electricity. We have local electrons from carbon atoms move throughout structure and now I'll leave it at that. Move throughout structure. For A part 3, why has it got a high melting point? Well, all these things we've talked about already. At high melting point, we've got lots of strong covalent bonds holding carbon atoms together. Require lots of energy to break. Boom, nice. Oh yeah, this is a long question, this one. So that was a question that was all about sort of covalent type here. We then go down here, so I've had that classic sort of question here. We then go boom, 4b. Oh no, we're on to titanium. It's a state, the type of crystal shown by titanium. Metallic. Why has titanium got a high melting point? Strong. See, it's just basically just regurgitating stuff. Strong attraction between electrons, or I should say really here, sod it. Delocalized electrons and positive ions. Requires lots of energy to break. Why can it be hammered into different shapes? Layers of, because it's in metal here, layers of ions can slide over one another. This is June 2012, by the way, I believe. And 4C2, why do they have similar strengths? And this is that thing that I mentioned earlier on. It was almost like I knew this question was coming. Why do they have similar strengths? Same metallic bonding as was present before. Okay, same metallic bonding. I said, oh, this question is just unbelievable. Now we go on to Ionic. lastly here, so ionic here, and I know this because I've got my metal, I've got my non-metal. Classic here, magnesium oxide. I'm not going to do the explanation because we've already done it, I think, with a previous one. Explanation, usual thing, I'll say it but I won't write it. Strong attraction between oppositely charged ions requires a lot of energy to break, and you can see that's a very, very high melting point. You know, over 3,000 Kelvin. It's very, very hot, and it just shows the strength of some of these bonds. Final one here. So we're now into question 5C. I'm going to do. Not going to do the rest of question 5. It is still bonding, but it's just a lot of repetition. Question 5 then C. Actually, I'm going to do this and 5D as well. Draw a diagram to show how the particles are arranged in aluminium. So straight away, 6 aluminium. Don't mess it up and do 4. Okay, minimum of 6. Do more if you want. Don't do less. There's 1, 2, 3, 4, 5, 6. Now, often they're not bothered about you getting the numbers right, but I'm a stickler, so I'm going aluminium being its 3+ as it is. It's lost all 3 of its delocalized electrons, or all 3 of its outer electrons become delocalized. I don't even normally get marks for the delocalized electrons. It's normally for a regular arrangement. If you draw them all over the place, you wouldn't get it, but the fact that I've drawn these in nice rows would be probably better actually if they were drawn closer together. But I want to really emphasise the idea of what my electrons between that. But provided they're in layers and we have I have a charge in the middle, that's going to get you 2 marks. Why is it malleable? Layers can slide. Finally, I like this one here, and this is one actually that I haven't mentioned, which is actually really, really bad. That's annoyed me, that. Why is the melting point of aluminium higher than the melting point of sodium? Well, this is the same goes for sort of ionic bonding questions as well. So aluminium forms a 3+ ion, sodium forms a 1+ ion. Here, 3 outer electrons that can become delocalized, 1 outer. So in the case of aluminium, so answer in terms of aluminium, greater charge and more delocalized electrons than sodium, therefore stronger, notice I'm being comparative, stronger attraction between, terrible there, between positive ions and negative electrons requires more energy to break. That's another kind of idea here. The idea of the and hopefully that would make sense anyway. The idea of the charge is being dependent or changing the sort of properties to an extent. Still high melting point for sodium, but obviously higher when it's aluminium. Going back to this question actually on magnesium oxide, where we've got Mg2+ and O2- compared to our Na+ and Cl-. This has a melting point of about, in Kelvin, about 900-ish thousand Kelvin. So you can see how much higher this is, and again the reason is that we have this double charge here, means that the attraction is stronger in the case of multiple charges than it is for the single ones, therefore more energy obviously is required to overcome it. But hopefully that would have sort of, that would have made some sense anyway. Right, that has been quite an intense, I think, quite information sort of dense video. Hopefully it's been of some help. Plenty of sort of questions at the end there. Any problems, stick them in the comments. But I do hope it's been of some help. And yeah, there you go. That's bonding.